Hello everyone. So in this talk, I will try to link how propagation of MGO helps in modulating the diurnal cycle of a particular place. Especially, this study was done in the maritime continent. So before going to the paper, I'm just trying to give a brief summary of what a diurnal cycle is. So basically, if you study the variability of any parameter within a time span of 24 hours, that is basically called the diurnal cycle of that particular parameter. Now, solar insolation is basically the primary governing force for the driving diurnal cycle of any particular parameter. So as a result of which parameters like temperature, rainfall, day source, storm, diurnal peak, and because of that diurnal peak, you get two important values for it. One is the amplitude of the diurnal cycle and the other is the phase of the diurnal cycle. Now, what generally happens is that the amplitude of the diurnal cycle is basically more higher in the land regions than that in the oceanic regions. And regarding the phase, that is the time of occurrence of the maximum diurnal cycle, what happens generally in the land regions, the diurnal cycle peaks in the afternoon or the evening time. But in the oceanic regions, it mainly peaks in the late night or early morning time. This is plot I have done in the from the IMS precipitation data set from ages 2000 to 2001, 2021 for the phase of the diurnal cycle. So you can see that most of the land regions, it peaks in the afternoon or the evening, but in the oceanic regions, mostly in the morning hours. But there are some regions like the province of the Himalayan regions and some of the coastal regions where these general phase occurrences of land and ocean does not hold. Then whenever we think about MGO, this picture from Madden-Julian 1971 paper, I remember this correctly. So this basically comes in our mind, which is one of the most important interseasonal variability of the monsoon rainfall, which is nothing but a eastward propagating system, which propagates at almost at the speed of say 4 to 8 meters per second. And this is basically found in the Indian Ocean and in the Pacific Ocean region. And the MGO is mostly active in the boreal winter times, that is the November to April time. So that's why in this paper they have discussed mostly in this boreal winter period of the maritime continent region. So there, what happens that basically this whatever this region you are looking at as a cloud, basically active MGO envelope they call, because this is connected with convection or rainfall region, and behind that there is a suppressed MGO envelope which comes just behind it, and they both moves in the eastward direction at this particular speed. Now, previously, many studies have been done in order to link the diurnal cycle of rainfall with MGO. So there are contrasting results like that. Some results show that because of MGO, there is an enhancement in the diurnal amplitude, in the amplitude of the diurnal cycle of rainfall. And in some studies, they have shown that there is suppressed amplitude of the diurnal cycle of rainfall because of the presence of the MGO on a particular region. So in order to tackle all these things, they have because in these papers mostly the data set was limited, as you can see that they were doing in some earlier. So that's why when the data set was updated, so they have done a restudy of that, and in order to understand what actually is the relation to whether it actually suppresses the diurnal amplitude or whether it actually enhances the diurnal amplitude at a particular place. So this is basically the paper which was published in 2014. So this is the study region which they have taken. This is called basically the maritime continent, what we call that is the mostly the islands that are in between the Pacific and the Indian Ocean. And these are the data set like precipitation. They have taken the TRIM 3B42 HQ precipitation because they have to combine the precipitation with that of the OLR. So that's why they have taken only this 3B42 HQ, and then they have taken the brightness temperature also from TRIM, topography and all this and there. And in order to express whatever the mechanisms, they have taken this wind and mean sea level pressure from this one. And as I have told that the period they have taken for the boreal meters, 40 boreal meters they have taken from this year to this. So as I have already shown in one of my plot also, like that how the and I have also told that the amplitude diurnal cycle is more in the land and the ocean. Here they have also found like they have started with the climatological picture of this over this maritime continent. So as you can see that as in most of the land regions, this is basically what the clockwise direction is the increase of the time as 12, 15, 18 is the time zone, and you can see that mostly in the day or in the afternoon hours the rainfall is maximum over the land regions. In the oceanic regions, it mostly peaks in the morning or the early morning or the late night hours. And also that you can see that this amplitude of this is basically the amplitude of the diurnal cycle. So over those amplitude. So on those mostly in the land regions the amplitude is highest, and far from the land regions wherever there are oceans the amplitude are negligible in comparison to those oceanic regions which are nearer to the land regions. So then there's a paper by Wheeler and Heldon, I think. So in there they have discussed the 8 phases of the MGO based on the PC1 and PC2 RMM1 and RMM2, and taking that similar method, they have divide these 8 phases of the MGO, and these are the various phases in anti-clockwise direction. They move from phase 1 to phase 8, and this is the brightness temperature anomaly over this region. So you can see that this active MGO envelope will be the regions with the negative brightness temperature, because negative brightness temperature suggests that there is convection over there. So the active envelope, this envelope moves in the eastward direction as the phases of the MGO propagates, and you can see that behind this active MGO there is this suppressed MGO envelope which also comes this side. Now this active MGO envelope especially occurs in this maritime continent region in the phases from 3 to 6 region, and mostly over this 4 to 5 regions. And also one thing to be noticed is that although there is a large spatial coherence in these regions, but there are some regions like say this region, or you can find somewhere these regions that although there is a huge positive envelope here, but there is almost zero or the opposite anomaly present over this particular region. That means there are some regions which is present in a positive anomaly region. There are some regions of negative anomaly regions also, or zero anomaly regions also. So we'll later on come to know why this happens. Now the same picture they have seen by means of the precipitation also, and you can see that they almost like the same as in case of the Euler we have seen. So it starts at it almost reach at the in the phase 2 it reaches almost in the maritime continent, and then it propagates, and this cycle repeats. But one thing is there that this spatial coherence is not as much as that it was found in the Euler case, and also what in that case what I was talking about, that presence of the opposite anomaly in within a say positive anomaly within a positive anomaly presence of a negative anomaly presence can be easily seen here. It can be more easily seen in this rainfall plot. So which shows that suppose this is the envelope. So from this envelope, if this envelope is propagating, some part of it is propagating earlier, or say it is priming the environment in order to enhance the propagation more faster. So later on, they will link these two with some mechanism. So now, because of this propagation, what happens to the diurnal cycle of that particular place? For that, they have averaged the daily mean precipitation rainfall for for a region, say Borneo region, and that's basically a land region, and they have compared this is the black color one is the climatological mean precipitation rainfall daily, and this red one is the phase number 7, which is basically the suppressed phase in case of this Borneo land region, and this blue one is the phase 3, which is basically the active phase in case of this Borneo region. So you can see that in the active phase, basically the mean daily rainfall is more as compared to the climatological mean daily rainfall, and the opposite case is in case of the suppressed phase, and also the amplitude of the diurnal cycle is enhanced in this Borneo region as compared to that in case of this dry or what you call the inactive phases. So then what they have done, that this is basically the so looking the spatial pattern, the anomaly of the amplitude of the diurnal cycle in all these places, in all these phases. So you can see that there is no eastward propagation of the anomaly of the amplitude of the diurnal cycle, just like it was found in case of the anomaly of the mean daily rainfall or anomaly of the brightness temperature. There is no propagation of the anomaly of the amplitude of the diurnal cycle. This means that the diurnal cycle is not propagating this side, but maybe the MJO is coming and it is affecting the diurnal cycle and it is increasing the or decreasing the amplitude of the diurnal cycle. It's not the diurnal cycle that is propagating, the MJO is propagating, and propagation of MJO is basically triggering or enhancing the diurnal cycle of the particular place. So, but one important thing was that in previous slide I forgot to mention here. So here the diurnal amplitude was highest mostly in those regions where the topography is high. So that means the topography plays an important role in determining the amplitude of the diurnal cycle. But the degree to which this modulation of the diurnal amplitude takes place, it does not depend on the topography. As you can see that it's not limited to only those places where topography features are important. It is also widespread over some oceanic regions also. So that means the topography is not at all important in understanding the modulation of the amplitude of the diurnal cycle. Now, they have done statistical significance tests and they have found that this 0.78 is basically the critical value of the correlation coefficient between the mean daily rainfall and amplitude of the diurnal cycle over this study region. So here we will see that these are basically the regions where the mean daily rainfall and the amplitude of the diurnal cycle are highly correlated. And if you remember, this is basically all those places where the amplitude of the diurnal cycle was high. So basically the diurnal amplitude is modulated only in those places by MJO where there is strong diurnal cycle. If there is no any strong diurnal cycle over that particular place, that place is not at all affected by the propagation of MJO. So now, in order to understand the phase relationship between different parameters, so here they have taken average over these three regions and say oceanic regions and land regions, they have averaged separately and they have checked out the three different parameters: brightness temperature, mean daily rainfall, and the diurnal amplitude, that is RD. So you can see that these and these are plotted against the various MJO phases, that 8 MJO phases. So you can see that the brightness temperature curve over the land and the oceanic regions are almost the same, and the peak of occurrence of their timing is also they occur only in the phase 4 region. But the values of the brightness temperature in the land regions will be lesser, as because we know that there will be more convective activities going on. So because of that, land region brightness temperature is less. But interesting thing is that the mean daily rainfall, it peaks a phase earlier than that it was in case of the brightness temperature. That means this envelope, before the envelope comes, the mean daily rainfall actually peaks. Now that is also true in case of the diurnal amplitude. That means the diurnal amplitude also peaks at almost the same time. So basically that MJO might have been modulating that diurnal amplitude, and because of that modulation of the diurnal amplitude, that mean daily rainfall is also getting affected by the presence of MJO. However, you can see that in case of the oceanic regions, this mean daily rainfall still remains the same. It peaks in the phase 4 only. So it doesn't matter, even though the diurnal amplitude is peaking a phase earlier, it does not matter to the mean daily rainfall, because we already know that the amplitude of the diurnal cycle in the oceanic regions is less. So even if it is modulated by MJO, it cannot change too much the mean daily rainfall. So the contribution to the mean daily rainfall is very, very less in case of oceanic regions. So now here they have basically calculated phases of all the locations, and they have made the phase difference between the phase of the mean daily rainfall and the brightness temperature. There's negative brightness temperature wherever maximum it occurs, and these hatched regions are the regions where this diurnal cycle is not important. So forget about those regions. So basically what this plot shows is that in most of these oceanic regions that far away from the oceans, there is very little phase difference. There is almost zero phase difference, which suggests that this OLR is a good proxy for precipitation in these oceanic regions. But those regions where this diurnal cycle was important, that is the amplitude was higher in those regions, they have at least one phase difference is there, a phase difference of 1. So that means that that OLR cannot be a good proxy for these regions where the diurnal cycle is important. So now they are trying to understand what may be the possible mechanism. So if just look at the picture of the phase. Yeah.
Can I go back to the previous slide? I didn't understand. Can you repeat?
Yeah, this means that in the places where the diurnal cycle is important, in those places, OLR cannot be a good proxy to check the mean daily rainfall because there is a gap of one phase, and this one phase is approximately 6 to 8 days. There's a gap. So, but in case of the open oceans, the phase difference is not much; it's almost 0. So that OLR is a good proxy for those open oceanic regions in order to understand. So in order to understand the mechanism behind those observations, like there is a envelope coming east side, but before that envelope reaches, there already is some heavy rainfall activities going on smaller scale. So in order to understand, they have taken the phase 2 where just the maritime continent, the active envelope of the MGO just reaches in that particular place. So it's just like some heating is going on in that place, and in that particular they have plotted the this is the pressure, surface pressure anomalies. So you can see that there is this extension of this eastward low pressure anomaly, which is like the Kelvin wave response over this one. And then you can also see that there is a northwestward and southwestward extension of Chutia, which is also a Rossby wave response type of thing. And these are the wind bars over this particular region. So because of this low pressure present over this particular region, what will happen? There will be an ageotropic wind component because these are surface. So because of the surface friction, there will be reduction in the Coriolis force, and because of the reduction in the Coriolis force, the ageotropic wind will basically oppose this divergence, which will cause convergence over these regions. So because of this convergence of these regions, and since this region is surrounded by warm oceanic water, so basically there will be a moisture convergence over this particular region when this phase 2 is just occurring. Now there is moisture convergence over this region. Now there is also some easterly winds flowing. Now because of this easterly wind flowing, as this easterly wind flow, it will strike over these high topographic regions, and because of those convergence and lifting up of the topography of the moisture towards the east side of this propagating MGO envelope, you can see patches of rainfall already existing in this particular region. And another thing is that, effect of moisture, and also when this MGO phase 2 is present in this particular region, there will be basically the positive Kelvin temperature over this one. You can see, so that means there will be clear sky. So whenever there is clear sky, we know that the insolation will be more. So as the insolation is more, that means the what you call convective activity will be more, moisture is also present. So this will help to sustain diurnal cycle more. So which basically increases the amplitude of the diurnal cycle of this particular places. Now because of the this moisture convergence and this wind bar and this clear sky, this all combines together in order to enhance the diurnal amplitude of those regions which are already existing on the eastward side of the eastward propagating envelope. So this is what the summary is this. So MGO modulates the diurnal rainfall by modulating the diurnal cycle of rainfall. So there is Thanangka, that means some part of envelope before it reaches, there is some already convective activity going on, which causes or increases the amplitude of the diurnal cycle, and it is basically because of the directivity between the Kelvin wave response and this frictional moisture convergence and the topography and the clear sky, which causes the enhanced diurnal amplitude ahead of the main envelope that occurs over this region. Thank you.
One question I have, the trim data you have used.
Yeah.
Does not do well over mountain.
Ah.
Have you used image?
I have not used this. Is
No. This is their work.
yeah.
Subsequently, nobody has used image. Image is better.
Yeah, I have not
Then
found I must using that place. Yeah.
because one weakness of data is over photography.
Yes.
Not that good.
Yes.
They are not made any count on that.
They have not met because this paper was in 2014. So at that time the 3 months.
Okay,
Yeah.
You should look subsequently NVIDIA looked at image. As well, we can compare down cycle image from last 10 years. but not last. So, there's overlap between.
Yes, it's 3
You
minutes.
can compare.
Yes, 2000 to 2014.
And I find that high resolution.
Yes.
So when you have mountains of that kind in Indonesia,
Hmm.
you need good resolution.
Yes, yes.
So IML is better.
Yeah.
Okay. Okay. Thank you. Thank you.